Hello everyone, my name is Kushal. I'm a PhD researcher in the Faculty of Aerospace Engineering at TU Delft. The title of my talk today is Large-Scale Flow Organization of Wall-Bounded Turbulence over Flush-Mounted Rotating Disks. The work has been performed with my collaborators Jakob Hussain and Dr. Woutijn Baars at the TU Delft. So let's begin with a broad question as to why skin friction control is desired. Many industries like the airline and the shipping industry consume fuel to overcome the drag forces that they experience. Up to 90% in ships and 55% in aircrafts is attributed to the skin friction drag that occurs at the interface of the object and the fluid. Due to the no-slip condition and the viscosity of the fluid, a boundary layer develops. And owing to the large Reynolds numbers, the flow is predominantly turbulent. And the aim of skin friction control is to reduce the shear stress or the slope of the boundary layer profile near the wall and reduce the deficit in momentum in the boundary layer flow, resulting in a benefit in fuel savings and subsequent emissions. One of the more well-researched active control techniques is transverse wall oscillations, also referred to as spanwise wall oscillations. This method involves introducing an unsteady oscillatory spanwise shear to the wall over which a turbulent boundary layer is present. The first experimental investigations were performed by Ladhari et al. In 1994, where hot wire measurements were performed downstream of the oscillating wall, where reductions in Reynolds stresses and the associated turbulent kinetic energy were quantified. Many studies followed, and in 2003, Quadri and Rico performed DNS simulations to produce a map of drag reductions for a turbulent boundary layer at a Reynolds number of 180. The figure on the right shows the drag reductions obtained for a corresponding time period and wall velocity of the oscillations, scaled by the near wall coordinates. Maximum reductions of about 45% were observed. And more recently, in an earlier work, high resolution planar PIV measurements were performed to assess the skin friction reduction near the wall of a turbulent boundary layer. The reductions that were obtained were in line with the earlier work of Quadri and Rico. This technique of spanwise wall oscillations, however, requires a mechanical system, and implementation at higher Reynolds numbers is a challenge due to the large frequencies of the actuation and the corresponding inertial forces. Recent studies at Melbourne by Marusic et al. Investigated the use of traveling waves of spanwise velocity both experimentally and numerically using LES to investigate the effects of these wall motions on the large scale features at the higher Reynolds numbers. The results indicated that the outer layer control appears to provide an increase in benefit at large Reynolds numbers, opening up research endeavors in this domain. The current study, however, focuses on the near wall control at low Reynolds numbers using flush mounted disks that have the benefit of the reduced inertial forces and the easier implementation. The concept of flush mounted rotating disks for flow control were first proposed by Keefe in 1997. The practical implementation of this actuation method is relatively easy and does not require any oscillatory motion. The concept was then examined using DNS of a channel flow by Rico and Hahn in 2013, who also produced a similar map of friction drag reduction as a function of the viscous scale disk diameter and the edge velocity of the disk. And maximum reductions of about 23% were found at a Reynolds number of 180. Following which, Visa and Rico investigated the potential of oscillating disks using the DNS of a channel flow and produced similar maps of drag reduction. An important parameter, which is the spacing of the disks in the spanwise and streamwise direction, were also investigated by Visa et al. And found to be maximum for a streamwise distance of about 1.5 and 1 disk diameter in the spanwise direction. However, it is important to note that experimental investigations are lacking for disks as a control concept. Therefore, the current work explores the wall-based actuation using flush-mounted rotating disks. Moving to the experiments were conducted in the open return low-speed wind tunnel at the Faculty of Aerospace Engineering in TU Delft. A boundary layer was generated using a flat plate with a width of 0.6 meters and length of 1.8 meters. The boundary layer was stripped with the distributed roughness elements, An array of 4 cross 3 flush mounted rotating disks were designed based on the optimal parameters from the work of Rico and Hahn. A disk diameter of 0.055 meters with a streamwise and spanwise spacing of 1.5D and 1.2D was manufactured. The images on the left show the array of motors during and after manufacturing. The variations in RPM were also checked and to be less than 3% of the mean. Here you can see the disks from underneath the wall. Moving on to the experimental technique, planar and stereo PIV measurements were performed in the XY plane over disk 4, in the wall parallel plane with cameras P2 and P3, and stereo PIV downstream of the disk array. The specifications of the PIV system is shown in the table below and is also included in the paper. Now moving on to the boundary layer profiles. The figure on the left and right represent the mean velocity and the Reynolds stresses respectively. These profiles were generated by streamwise averaging in the XY plane from the planar PIV data over the streamwise extent of the last disk. The experimental data of both the mean velocity and the Reynolds stresses show a good agreement with the DNS data in the inner regions. For the case of optimal control, that is W plus of 10, the velocity data is only available for Y plus less than 0. Y plus less than 100. When inspecting the mean velocity profile, it is evident that the velocity decreases below Y plus 10. This indicates a reduction of the average friction drag at the center location over which the measurements were taken. Moreover, a peak-to-peak reduction of 30% in U prime occurs, together with significant reductions in the magnitudes of U prime V prime and V prime V prime below Y plus of 100. Note that our study is the first demonstration experiment, but a direct determination of the reduction in friction drag was not reliable. Nevertheless, in the subsequent slides, I continue with a description of how the rotating disks affect the large-scale flow organizations. For this, we inspect the other two PIV measurement configurations, starting with the wall parallel plane. As you can see here, the normalized streamwise velocity in the wall parallel plane at a height of Y plus 70 shows high and low momentum pathways. It is evident that the increase and decrease of the velocity in these low and high momentum pathways is strengthened when moving towards the case of W plus 25, which corresponds to a higher RPM of the disks. Also, in order to make a qualitative comparison of how the mean flow is organized in the spanwise direction, the wall parallel planes, the data from the wall parallel planes were streamwise averaged in the region downstream of the last row of disks, where the X by D lies between 5.5 and 7. The spanwise profiles for all the cases are shown in the figure on the right. It can be observed that the regions of velocity deficit in the case of control is narrower than the region of the velocity surplus, but is more intense. And averaging the spanwise velocity over one periodic unit, that is the disk diameter, yields three vertical lines, which indicate a monotonic trend towards a higher mean velocity when W plus increases. Also, from the plot of the Reynolds stresses, region of high and low stresses is observed in comparison to the uncontrolled case. When focusing on the intense patches of U prime, it is observed that they are located just downstream of each row of disks. Their spanwise location also depends on the rotational direction of each row of disks. That was for the wall parallel plane. And now moving to the cross plane downstream of the array, which is also represents both for the uncontrolled case and the optimal control case, the fields of the mean streamwise velocity and the Reynolds stresses. Also, it is important to note that the spanwise range covers the span of the disks, which is located at z is equal to 0. In comparison to the spanwise invariant mean flow of the uncontrolled case, a clear modulation of the velocity isocontours appears at W plus equal to 10. This also reflects the same observations that were made in the previous slide of the wall parallel plane. The location of the wall parallel plane is also shown with the horizontal dashed lines. it is clear to observe that for a given height above the viscous sublayer, a higher mean velocity occurs in the disk center, while the flow velocity is lower at the edge of the disk. Thus, the flow over the center of the disks exhibits less deficit in momentum. Now, moving to the topology of u prime u prime, it is also clear that for z by d between minus 0.25 and plus 0.25, the Reynolds stresses is constant in span and suppressed in comparison to the uncontrolled case. An interesting observation at this point is that the large-scale flow organizations over the disk array is strongly reminiscent of one found over other wall-bounded turbulent flows with span-wise varying surface conditions. Now, moving on to the conclusion, uh, the whole work consisted of an experimental investigation of the large-scale flow organization over an array of flush-mounted disks, which was under a turbulent boundary layer. Different conditions of the PIV measurements were employed to reveal that uh, low and high momentum pathways were also established in the flow due to the span-wise varying friction drag. It is also postulated that the actuation mechanism using flush-mounted rotating disks will have a large control authority for the organization of large-scale flow features, and this can be beneficial in terms of friction drag reduction techniques at higher Reynolds numbers. With that, I would like to thank you for your attention, and I'm happy to answer your questions.